Seaborn is a statistical plotting library in Python. It's built on top of matplotlib, which means when you run a Seaborn command, it runs a set of matplotlib commands under the hood. It's built with beautiful default styles for the graph, which makes it easier to read and comprehend. Seaborn is designed to work very well with pandas data frame objects, and therefore it's the go-to library for plotting data in Python. To install the Seaborn package, you would need to use the commands conda install Seaborn if you are using the Anaconda prompt, or otherwise pip install Seaborn if you are using the command prompt. So Seaborn can be used for analyzing different types of data by using different types of plots for numerical data, for categorical data, and even for data in matrix format. So let's start by importing our libraries and some data to work with. So here we will import numpy snp, import pandas spd, import matplotlib.pyplot splt, import seaborn as sns, and we will run a one-line code matplotlib space inline. So this last line %matplotlib space inline, this will help to see the visualizations in the Jupyter notebook. Next, we will upload the dataset. So Seaborn comes preloaded with some datasets which we can use for practice purposes. So one of such datasets is called tips. To load the datasets, we can run the command sns.load dataset and just pass in the tips. So we can check the doc string here. It says load an example dataset from online repository. So this function provides quick access to a small number of example datasets. So we can use it for our practice as well. Let's run this. It will load the dataset. So let's check the head of the dataset. So this is our dataset. So it looks like it's from a restaurant. We have the total bill and we have tip data, and then we have some other categorical data. Now let's check the info. So in total it has 244 entries, range index going from 0 to 243, and 7 columns. Total bill, tip, sex, smoker, day, time and size. There are no null values here, and as we can see, the first two columns, total bill and tip, are float data. Then the next four are categorical data, and the last column seems to be integer data. So now that we have our data, let's move on to the distribution plots. So these plots allow us to visualize the distribution of a dataset primarily for the numerical column. So distribution plots are for the numerical data, which will be for floating data and integer data, and this allows us to visualize, if you can consider all of these columns as variables. So for this column total bill, let's say we see some of the bill here, but we want to know the distribution of this column, that where does the most of the bills lie. If you go through the data one by one, it will be very difficult, but plotting it by visualizing it, we can easily look at that plot and analyze where does the most of the data lie. So we have different kinds of distribution plots. We have hist plot, which is basically a histogram. This is for univariate data. Then we have joint plot, which is for two different variables, so kind of x versus y. Then we have pair plot, which is for bivariate data for all the pairs of numerical columns in a data frame. We'll see that. Then we have rug plot and we have KD plot. These are again for univariate data. We'll see that once we get there. So first we have histogram, which shows the distribution of a univariate data. So to plot this, let's say for this data set, we want to understand the distribution of this total bill. So sns.histplot, as you begin typing, press tab, and we can check the doc string here. So we need a data, then we need either x or y. Because this is univariate data, we need to pass in only one of x and y. If you pass in x, the graph will be vertical. If you pass in y, the graph itself will be horizontal with base on the y-axis. So let's plot this total bill. Let's run this, and see, this has plotted a histogram for that entire column. So as you can see here, on the y-axis we have count, and on the x-axis we have this total bill data. So if you look at the distribution, most of the bills are between $10 and $20, and as we go higher, the number of bills gets lower and lower. And that is intuitive, right? There would be very few people who would be spending more than $30 for a lunch or for dinner. Of course, there's a variable for number of people as well, which is the size of the group or size of the party. We will get to that later, but for now, if you want to look at the distribution of the total bill, most of it is between 10 and 20, with very little data before that and after that. Now let's check out some other parameters here. We have a bin parameter, which is given auto by default. So let's say you want to divide the entire distribution into 20 bins or 10 bins. So let's run that. Let's go for 10 bins first. We want lesser number of bins, or if you want to increase the bins count as well. So it will give you a very minute distribution, but not all of the bins will have data here. So it really depends on the kind of data you have. And there's another parameter. If you take a look, we have this KDE, which is given false by default. So if you want to plot the KDE plot, we'll come to the KDE plot later, but if you want to plot the KDE plot on top of the histogram itself, you can return true for this, and this will plot a KDE plot. KDE plot is similar to bell-shaped curve. KDE is short for kernel density estimation, and it will give you a nice distribution of the data here. And we can also use the hue parameter here, and let's pass in this X column for this. So right now the data selected is only for that one column, so we need to select the entire data frame here. So data will be tips, and then our X would be this total bill columns. So now we can select this, and as you see here, we will have two different histograms. One is in blue color, which is for male, and then we have this in orange color, which is for females. And we have the overlap here as well. If you remove the KDE part, KDE parameter, you can see it clearly here. Let's remove this. Now this is the simplest form of a histogram. It is easier to read, and you can easily see the distribution of a univariate data here. Next, we will move to joint plot. Now, rather than looking at the distribution of one column, let's say you want to understand the relationship between two different columns. For example, for this data set, we want to know what is the relationship of this tip with the total bill column, because intuitively you think that people who have a higher bill will give higher tip amount, right? So we want to visualize that. So to compare the two data together, we have something called joint plot, which is used for bivariate data, that is to compare two variables or two numerical columns from a data frame. It will plot histogram for both data separately and will show x versus y comparison as well using kind parameters. So let's plot this quickly. We'll pass in our data, which is tips. Then we will pass in the column which we want on the x-axis. So let's say on the x-axis we want total bill column, and then on the y-axis we want the tips column. So let's plot this. Okay, so this column name is tip, not tips. So here, as you can see in the joint plot, in the middle we have this x versus y data, that is total bill versus tip, and this by default has scatter plots. And then for both data set, for total bill, it will plot a histogram here, so we can look at the distribution of that data. And then we have a histogram for tip as well, we can look at the distribution of that data as well. Let's first talk about the histograms. As you can see, most of the bills were between $10 and $20, and then the count of the bills went lower as we moved up in the dollar amount. Similarly, for the tip, most of the tips were between $2 and $4, and there's very little tip in the higher amounts. But here, most importantly, by using this scatter plot, we can see there is a rough relationship between total bill and tip. As the total bill goes up, the amount of tip goes up as well. Now let's say for the same graph, data is equal to tips, which is our data frame. Then on x-axis we want total underscore bill, and on the y we want tip. Now there's another parameter here. Called kind, which is by default given as scatter. So for this kind parameter, we have these different options given here. Let's by default we have scatter here. Let's check out the other options as well. So let's check this hex bin first. So what this hex does is it divides the entire plot into many different hexagonal bins, and then based on the number of points inside the bin, it gives it either a darker color or a lighter color. The more number of points inside a bin, the darker will be this hex bin. So we can look at the distribution of the data here. Similarly, if you can use reg, which is short for regression. So this regression will again plot scatter plots, but will also draw a regression line through the points. This regression line shows us the rough probability of tip being in the particular range for a particular amount of total bill. This is also used for predictions. Let's say if the next customer is likely to have a bill of $50, his tip is likely to be in this range of $5 to $6. However, that may not always be the case, as you can see from this data points. Another one is KDE, which will draw some curves like this. And if you check here, we have some other parameters. Again, we have height, which is for height of this figure, ratio, which is basically the ratio of height to width. So you can adjust these things if you want. So here we saw how to analyze univariate data using histograms, and then we saw how to analyze bivariate data, that is two variables, using a joint plot. Now we have another plot called pair plot. A pair plot plots a pairwise relationships across an entire data frame for the numerical columns, and supports a colored hue argument as well for categorical columns, as we have seen earlier for the histogram. So what this will do is it will plot pairwise data for all pairs of numerical columns in a data frame. So let's see this. We just need to pass in our data frame here, and it will automatically plot this for all pairs of numerical column. Now depending on the size of the data frame, this could take a while if we have a very large data set with a lot of data. For now, let me zoom out a little bit so we can see this better. So here we had only three numerical columns, which were total bill, tip, and size of the party. So on the x-axis we have all those three, and on the y-axis we have all three numerical columns. So total bill versus total bill is just a histogram, as it is a univariate data. Then total bill against tip is a scatter plot, And total bill, again size, is a scatter plot as well. Here this data was discrete, it wasn't continuous, it was just integers 1 2 3 4 5 6, and so it has plotted the bill for each of those size here. So the benefit of using pair plot is we don't have to analyze each numerical column or a pair of numerical columns separately. We can just plot a pair plot for a given data frame and see the univariate distributions of all of those numerical columns, and then we have the comparison of each column versus other numerical columns. So if you want to read this same scatter plot the other way around, if you want the total bill on the x-axis and tip on the y-axis, you can look at this. Then this is tip versus tip, so a histogram for that column. Similarly, we have a histogram for size as well. Now here, if you check the doc string, we have a hue parameter again, and then we have a palette. Palette is for colors, color combination. And then once again we have this height and aspect ratio. Aspect is just the ratio of height versus width. So you can use those parameters as well if you want to change the size of the entire diagram. So for you, let's go with this 6 column, which is categorical data for male and female, and it will separate out the data for each of these plots based on this category. And you see we have this blue color for male and orange for females. We have a palette. You can use the palette parameter here, and if you want to use a different color combination, one of those color combination is cool warm, and we have this in lighter color. It's the same blue and orange color for cool warm. You can use magma as well. This is slightly different color combination here. Then let's check summer, which is more on the greenish side, and we have many different palette options available. You can google for color combinations for Seaborn. It will give you official documentation for the Seaborn, and you can check all of the palette options available there. Next we have rug plot. A rug plot simply puts a dash mark for every data point on a univariate distribution. So for one column, let's say for the total bill, for each of the data, it will put a dash mark on the x-axis. So let's quickly check this out. We have this rug plot, and let's say for tips, we will pass in this total underscore bill. So let's pass in this and see for each of this total bill, each data point, it will put a dash mark there. So these are basically building blocks of a KD. You won't be using rug plot just by on your own, but it's good to know how to plot it. Now let's move on to the KDE plots. The KDE plot replaces every single observation on this rug plot with a Gaussian normal distribution curve centered around that mark. So for each of these dash marks, it will create a normal distribution curve and then adds up the y values for all of the x values on the plot. So now, as you can see on this diagram, here for the same data set, we have two different figures here. On the left one, we have a histogram, and on the right one, we have kernel density estimate, which is constructed using the same data. So here, if you look at this bin, there are two data points inside this bin. So this bin is higher than the other bins, all of which has a single data point. Now for KDE plot, for each of these data points, imagine this red curves which are normal distribution built around each of the data points. So the peak of this red curve would be at this data point, and then it will taper off on both directions. Now for KDE estimate, all of the values of y at a particular x values will be added up, and this will give us a smooth blue curve which will be the kernel density estimation. So basically, what is the density of that particular kernel on the x-axis? It will give us an estimation. So on each of these data points, a normal distribution curve is built with the mean of that data and standard deviation of 1.5. And then for each value at the x-axis, the corresponding y-axis for each of these normal distribution curves is added up and is plotted using this blue curve here. So to plot this, we can use sns.kde plot, pass in your data, which is tips, and then on x we can use total underscore bill, and it will give us a KDE plot. Now here we can also plot the KDE plot equal to tips and x is total underscore bill. So here we can plot both KDE and rug plot together as well. So here we can plot both KDE and rug plot together as well, and you will get this plot. This is useful for analysis of univariate data if you want to know the rough estimate of where a particular data could lie. However, if you want the exact distribution of the data, you should use histogram. Next, we will move on to the categorical plots. So these categorical plots allow us to visualize the distribution of categorical data in a data frame. For example, there could be a column for sex in a data frame, and the data for that would be male or female. Similarly, there could be a column for day, and that could be Sunday, Monday, Tuesday, etc. So for to analyze the categorical data, we have a few different kinds of plots available in the Seaborn. We have bar plot, count plot, box plot, violin plot, strip plot, swarm plot. Let's look into this one by one. So the first is a bar plot. A bar plot allows us to aggregate the categorical data based off some functions like sum, mean, median, max, etc. By default, it will return the mean. This is similar to the group by function in pandas. So if you are using a pandas library and you want to find out the mean of different categories of data, you can use a group by function and use the mean function with that. However, if you want to visualize that data for each of the categories in a column, we can use a bar plot. So for a bar plot, we can use sns.barplot, pass in your data, which is tips. Then on the x-axis, we want the categorical data, so let's use the 6 column. And on the y-axis, we want the total bill column. So let's plot this. And what this plots is, we have 6 on the x-axis and total bill on the y-axis, and what it returns by default is mean. So for male, it is the average of all the bills, which is just above $20, and for females the average was just below $20. It's closer to $18. So if you want the exact data, you can use the group by function along with the mean function using the pandas library. However, if you want to visualize for all the different categories, you can use this visualization bar graph. Now if you look at the docstring here for the bar plot, we have our data and then what we want on the x and y column. Then we have a hue parameter as well. If you want to separate it by another category, we have hue for that. Then we have an estimator parameter, which is by default given as mean. So let's say in place of mean, you want in place of mean, you want to see the total bill for both male and female. You can pass in the sum function under the estimator parameter, and this will return the sum of the total bills for male and female. Similarly, if you want to check the standard deviation, We don't have a standard deviation function in Python, so you can use numpy for that, numpy.std, and it will return you the standard deviation for that. Now if you want the count of both male and female in that series or in that column of the data frame, we have a count plot for that. A count plot is essentially the same as bar plot, except the estimator is explicitly counting the number of occurrences. So this is similar to value count function in pandas. So for this we can use sns.countPlot, pass in your data set, and then on the x-axis we will pass in the categorical column for which we want the count of the categories within that column. So for sex we have male and female, and it will give us the total count. For male it's less than 160 and we have around 90 females. This is same as using a value count. So let's say on the steps we have the sex column, we can use value counts here. So this will return 157 for males and 87 for female. And we can use the count plot visualization here to get the same data. Let's check another one. Let's say you want the count of the day column. So data is equal to tips, x is day. So here it will give us total count of the different days within this day column. So as you can see, this is different from bar plot because here we need only, this is only for univariate data. For the categorical data, it will give you the total number of each categories within that univariate or within that same column. But a bar plot will use that category and it will relate the data with some other numerical data in another column, and we can use that to find either the sum or the average or some other description of the data for these categories. Now next we have a box plot. A box plot is used to show the distribution of categorical data, just like we have histogram for the numerical data. If you want to see the distribution of the data for each of the categories, we have a box plot for this. A box plot is used to show the distribution of a categorical data. The box plot or box and whisker plot shows the distribution of quantitative data, that is numerical data, in a way that facilitates comparisons between variables or across levels of categorical variable. The box shows the quartiles of the data set while whiskers extend to show the rest of the distribution. I will explain this when we plot the box plot, except for points that are determined to be outliers. So let's plot one. We have the box plot command here. Pass in your data, that is tips. Then on the x-axis we want the categorical data. Let's say we want to see the data by day, and on the y-axis we want the total bill. So let's plot this. So here you see that on the x-axis we have the categorical data for the day column. We have Thursday, Friday, Saturday and Sunday, and on the y-axis we have total bills. So for Thursday we have the distribution of all of the bills which are available in the data set. Similarly for Friday, Saturday and Sunday. And this is a box and whisker plot. And then in the circles we have outlier data points. So what we have here is, this is the minimum data point, this is the max value of the data point except this outliers, and then we have this quartiles which is 25 percentile points. This is the median line, that is 50 percentile, and then this is the third quartile. First quartile, second quartile and third quartile. Third quartile is 75% line. So this is the max value, 75 percentile or third quartile, 50 percentile or median, 25th percentile or first quartile, and the minimum value here. So it will form a box for data within 25th to 75th percentile, and will extend whiskers for data between the 75th and 100th percentile, and similarly on the lower end for 0 to 25th percentile. And some of the data will be considered outliers, that this data is different from most of the data within this group. See here, except for points that are determined to be outliers using a method that is a function of interquartile range. So if you look for Friday, we have one data point which is completely different from the rest of the data point. So there is a function which is used to calculate this interquartile ranges. You can read, if you want to read, you can Google this interquartile range. If you want, you can Google interquartile range and read more about it. But that function is used automatically by Python or Seaborn to determine these outliers. These outlier data points are very different from most of the data in the group, and if it is included to study the entire data set, then it will completely skew our understanding of the most of the data here. So for an example, let's say if you are calculating per capita GDP of a country, and if you include the income of billionaires in that as well, the per capita GDP will be a higher amount than if you exclude the billionaires and then calculate the per capita GDP of the remaining people. You will get the actual distribution, actual income distribution of the people, which will be much lower than the average GDP per capita figure you will find on Google, because billionaires are just a small number of people who have very high income, much higher than the rest of the group, and therefore they skew the average for the entire group just on their own. So if this is a graph of those billionaires, it's important to identify those data points and look at the rest of the data separately from these outlier points. Now if you want to give a color to this graph, we can use the hue parameter here. Hue is obviously for categorical data, but if you use the hue with the same category which we have here, it will use a nice color combination for this graph. Now let's say you want to use another category along with this graph itself, so you can do that. It's on X we have this day data, on Y we have the total bill for the distribution of the bills for this category, and now you want to separate the data for sex category as well, so we can do that here. So here we have blue for male and orange for females, and for each day for each category we will get separate distribution for males and for females here using this box plot. Now next, let's move to violin plot. A violin plot plays a similar role as a box and whisker plot. It shows the distribution of quantitative data across several levels of one or more categorical variables such that those distributions can be compared. Unlike a box plot in which all of the plot's components correspond to actual data points, the violin plot features a kernel density estimation of the underlying distribution. So basically, a violin plot is very similar to a box plot in that we can see the distribution of a numerical data for categorical data on the x-axis, but the difference here is whereas the box plot had the actual data points, the violin plot will plot a KDE graph for each of the category for the underlying distribution of data. So let's plot this. The parameters will be same as we had for box plot. So let's plot this. Once again, if you want to use the color palettes, we can pass in a hue argument which will be same as this categorical data we have on the axis. So here, as you see, rather than the box plots which corresponds to actual data point, actual dollar amounts on the total bill, we have a KDE plot which shows the estimation of the total bill for a particular value. So if you look at the thickness here, we know most of the data lies between $10 and $20. Similarly, as you go from 20 to 30, the graph drops off here. You have to look at this in a horizontal way. If you want, you can also change this to Y and change this to X, and that will make more sense. So now we have our categories on the y-axis and the total bill on the x-axis. So you can see for Thursday, most of the data is between $10 and $20, and as the total bill goes higher, the graph will go down, and we have the mirror reflection of that here as well. This total thickness represents how many data points lies between $10 to $20, then from $20 to $30. Similarly for Friday, Saturday and Sunday. So you can use this whichever way you want to read it. Now if you want to further divide it, let me copy this. If you want to further divide this for another category, let's say you want to read this for different sexes. Here using the hue as the sex category will differentiate the data for both male and female. Now if you look at the docstring here, we have this data parameter, then XY hue. If you go down, we have the palette. If you want to use a different color combination, you can pass in the palette here. And then we have this split parameter, which is given as false by default. Let's pass in true for that. And what this will do is it will split the violin plot into two different categories for male and for female. So whether you want to use the graph in this way, where the left hand side of each of the violin plots here is for male data and the one on the right hand side is for females, or if you pass in false here, you will get separate much thinner plots for both male and for female. Now next we have a strip plot as well. This strip plot is very similar to the violin plot. The strip plot will draw a scatter plot rather than this continuous curve. The strip plot will draw a scatter plot where one variable is categorical. A strip plot can be drawn on its own, but it is also a good complement to a box or violin plot in cases where we want to show all observations along with some representation of the underlying distribution. Now if you go back to the violin plot, I forgot to mention here, if you use a violin plot, you will get a small box plot within that violin plot as well. So a difference to notice here is that while box plot ignores the outlier values, the violin plot includes all data values for each category, and that's why you see very thin plots at the extreme ends of the violin plot. So we will use SNS.strip plot for this. Pass in your data, which is tips. On the x-axis, let's say we want day. On the y-axis, we want total bill. Let's plot this. And rather than a violin plot, which had the distribution of the data, this will give us the exact data points using a scatter plot. If you want to use different colors, once again, you can pass in the hue parameter here for the same category. Now remember, if you pass in the same category as you have on the X, it will just change the palette, color palette for this. If you pass in a different category, it will split the data for that category for you. Now if you look at the docstring, we have our data X and Y hue, and then we have a parameter called jitter and dodge. Now here, let's say you want to use a separate category for sex. Now you have this overlap between the data points for both male and female, right? So for that, to separate that, we can use a dodge parameter and pass in as true, and it will separate the categories for both male and for female data. Now apart from this, we also have a jitter parameter. What the jitter does is it will form all of these data points in a straight line. So let's check this out. We have data called tips. On x-axis we have day, on y we have total bill, For hue, let's go with day for now, and then we have jitter. Let's make this true. So when jitter is true, jitter is given true by default. Jitter is given true by default. When jitter is true, we have data like this. All of the categorical data, all of these data points are spread out, so you can see each of the individual data points. If you pass false for this, all of the data will form in a straight line. If you want to see it like this, if you want a distribution like this, you will get this. However, it's very hard to differentiate between individual data points here or here. If you want to separate this for a different category as well, you can do that. So now all of the data are in straight lines. We have use hue for a second category, and then jitter is false, so it will not. If you pass in as true, it will separate out each of these data points. And dodge is true. Dodge plays the same function in strip plot which split plays in a Boolean plot. In a Boolean plot, if you pass split is equal to true, it will split this Boolean plot in two different categories for male and female. Now next is swarm plot. So let's plot this and then we will see what this is. Data is equal to tips, x is day, and y is total bill. So you can see the swarm plot is similar to a strip plot, but the points are adjusted only along the categorical axis. So rather than lying one above the other, the data points will be adjusted outwards along the categorical axis. The data points will be adjusted along the categorical axis so that it doesn't overlap. This gives a better representation of the distribution of values. So here we know that around this point there are more data sets, although it does not scale as well to large number of observations. However, if let's say there are millions of data in a data set, then Seaborn won't be able to plot each of those data within this small figure, and so it does not work very well with large number of observations in a data set. Now just like the strip plot, we can add in a hue argument here. If you want to use different color combinations just for this data, pass in the same category and it will have different color combinations here. If you want to use the same graph for a second category as well, you can do that. And similarly, just like the strip plot, for the swarm plot we have our dodge parameter as well, so you can pass in true for this and it will separate out the second category for each of the categories on the x-axis. We don't have the jitter parameter for the swarm plots, as all of the data points will be separated out from each other. What we can also do here is we can plot both swarm plot and Boolean plot together. So let's say we have our Boolean plot, data is equal to tips, x-axis is day and y-axis is total bill. And for hue I will pass in the same category as I want different data here. Now I will plot a swarm plot using the same parameters here. And what this will do is it will plot the swarm plot over the Boolean plot. So let's change the color for the swarm plot here so we can see this to black. So here it will plot the swarm plot over the Boolean plot, so we get to see the distribution of individual data sets and we also get the distribution plot here. Now be careful with using the plots like Boolean plot, uh, strip plots, swarm plots, as these are complicated plots. So when we are plotting these categorical plots, this Boolean plot, strip plot and swarm plots are very complicated plots, and only people who are aware of these plots can understand what's happening in that. So if you are doing your own analysis or you are plotting this to be shared with other data scientists or data analysts, you can use this graph. But if you are presenting something to higher management, it's better to stick with these simple plots like bar plot, count plot, and box plot. The management people are more used to these kind of plots, and they will it will be easier for you to get your point across to those people. If you are using a swarm plot along with a volume plot to a management person who has never seen these plots earlier, it will be very hard for them to understand whatever you are trying to convey to them. Now we have a last plot in the categorical plots column. Okay, this goes here. And then we have a cat plot, which is a general form of categorical plot. So rather than using different names of the plot like box plot, bar plot, swarm plot, volume plot, we can just use cat plot and pass in a parameter called kind for the kind of plot we want. So we can use sns dot cat plot, and if you look at the parameters here, we have our parameters for data, for x, for y, for hue, for color, and then we have a kind which by default is given as strip. So let's plot this quickly. Let's say for x we will have day category, for y we will have total bill column, and by default it will plot a strip. However, if you want to change this, we can use bar as well, and so it will plot a bar plot. If we pass in box, it will plot a box plot. Similarly, if we use violin plot, it will plot a violin plot here. So if you want, you can use cat plot, but then you will have to kind of define what kind of plot you want to plot. However, it's much easier to directly use the plot name here like bar plot, count plot, box plot, etc. So that's all for the categorical plots. Next we will move to matrix plot. Matrix plot allows us to plot data as color encoded matrices and can also be used to indicate clusters within the data. So the data for matrix plots has to be in a matrix form where both the index and column have some variables or categorical data, and the matrices have some sort of numerical data which relates to both index and column. So basically the data has to be in a tabular format where both the index and column are categories. So the data relate to both index and column in some form. The example of a matrix could be a pivot table, or it could be a correlation. If you find correlation between different numerical columns in a data set, the whatever it returns will be in matrix form as well. So for this we need to import a new data set. So in Seaborn we have a data set called flights data. So let's use sns.load underscore dataset and just pass in the keyword flights. If you want to look at the doc string, we need to pass in the name, and then we have some other options which you can ignore. Let's check the head of this data set. So here we have only three columns. We have a year column, we have a month column, and we have passengers. So this is basically the number of passengers for some airline for this given year and month. So let's look at the info to understand this data set in more detail. So total there are 144 entries ranging, row index goes from 0 to 143, and just three columns, no null values. We have integer for the year and for passenger, and we have month. So this data we can arrange in a matrix format. So let's say we will use pivot table. Here we will name the variable fp. What we will do is flights dot pivot table, and here we need to pass in the values, index and column. So for index we will use the year column. For column we will pass in month, and for values we will pass in the passenger. So let's check this data. So here what we have now is we have a index which is for years, which goes from 1949 to 60. Then on the columns we have all the months, which goes from Jan to December, and then we have all the remaining data arranged in a tabular format. So you can see that for year 1949, for January there were 112 passengers, 118 for Feb, 132 for March. Similarly for the year 1956, let's say for December, there were 306 passengers. So now we have our data in a matrix format. Now this is a very complicated table. You cannot just, it's not very intuitive. You cannot just read it and say where the data was high and where the data was low. You cannot infer information. This is a very complicated table. You cannot just infer information just by looking at this. So it's much easier to use a heat map here. The heat map will just put colors on this each individual cells to make it visually understandable and intuitive. So what we can do here is sns.heatmap, and for data just pass in this table. The name of the table is FP, so just pass in that, and here you can see the table has now been encoded with a color combination, and we have a scale here. What you see in the scale is we have a lighter color for higher numbers, which is around this part of the table, and we have lower numbers for, we have darker colors for lower numbers, which is at the top of the table. This is not very intuitive. I like to change this. So if you look at the parameters, we have a CMap parameter, which is for color mapping, the mapping from data values to color space. So what you can do is use this CMap, and you can use any color combination which you want. Let's say cool warm. So here cool warm has blue color, which is lighter for the lower numbers, and then it has red for darker. But if you look at this in the middle, it is very light, and it's very much darker on the both ends because it's divergent. So let's use another palette here. Let's use magma. So this goes from lighter to darker, but it's on the downside. We can use magma underscore R to reverse this color combination here. So now the lower numbers are lighter in color and the higher numbers are darker in color. And now this table is much more intuitive. You can see most of the passengers are around the summer months of the year 1960. As we go from left to right in the table, most of the passengers would be in the middle because most people would be traveling in the summer months for vacation, and lesser number of people would be taking flights in winter months like Jan, Feb and November and December. So there should be lesser passengers in those months. Similarly, as you see, as we go from top to down, from the year 1949 to 1960, we will get more and more passengers in the later years than in the earlier years. That's why you see the 1949 and 50 years are much more lighter compared to the rest of the table here. We can plot heat map for our earlier table as well for the tips data set. For the numerical columns in that data set, we can find a correlation. So let's call that data frame TC, and let's find the correlation for that. Could not convert string to float. It is trying to find the correlation for the string columns as well. And here if you see, we have a parameter numeric underscore only, which is given as false by default. It used to be true earlier, but now they have changed it to false. I'm not sure why they did it. But if you just pass this and now check this data frame, this is a correlation data frame just for the numerical columns. So obviously the correlation for total bill, which is univariate, is 1. Then the correlation of total bill with tip is 0.67 and with size is 0.59. So there is moderate positive correlation between these variables. So we can plot a heat map using this data. And here once again the data goes from darker to lighter. So you can pass in a Cmap for this. Let's use magma color here. And let's use the _r reverse for this color combination. So now it goes from lighter to darker. Now there's another parameter here which is called annote. So if this is true, it will write the data value in each cell. So let's pass that. Annote is true. So the values you see here in this table, those would be written over here as well. So it makes it easier to analyze. We could not have used annote here for this table as there are a lot of smaller box and it will become very complicated if you put annote here. So you cannot read this. So it's better not to use annote with heat maps like this. But here we have much bigger boxes, so we can use annote with this heat map. So next we will move on to the cluster map. Cluster map is very similar to heat map, but what it does additionally is it clusters the similar data together for both row and column. So it uses a hierarchical clustering to produce a clustered version of heat map. So the data which are similar will be clustered together. It will cluster all the rows together and all the columns together based on similar data in the matrix. So we have our flights data once again. Let's see, check this FP. Let's say we want to use cluster map for this. So let's pass in our data, which is FP. Now the size of this is very big. We can reduce the figure size here. We have the fixed size parameter given, which is 10 by 10 by default. So we can, let's go with 7 by 7, or let's go with 5 by 5 so that it fits in here. Let's try 6 by 6. This is too small. Yeah, so now it fits in nicely. Once again we want to change this color combination as the higher values are denoted by lighter color, which is not very intuitive. So I will go for magma _r. _r at the end of any color combination or this color palette reverses the palette the other way. So if for magma the lighter color was for the higher value, now the lighter color would be for lower value. So compared to heat map, when we plotted the heat map for this flights data set, here you can see on the y-axis the years went down from 1949 incrementally to 1960, and similarly the month went from Jan, Feb, March all the way to November and December in the heat map. But when you see that same thing in the cluster map, we have Jan, Feb, and then November is combined between Feb and March. Similarly, December comes between March and May, and then April comes after it, and the summer months like July, August are put together, and this is clustered along with the fall and spring months of June, October and September together. Similarly, on the y-axis as well, you can see the years are not in the same manner going from 1949 incrementally to 1960, but the years 1959 and 60 are clubbed together with are clubbed together in the middle, but the other years are arranged separately. So here we have another parameter called standard scale. If you pass in 1, so it will change all of these without this standard scale. If you see, we had this colors intensity going from 200 to 600. If you use this standard scale, it will go from 0 to 1. So it will standardize all of the colors here. So next, let's move on to the grids. Grids are used if you want to further customize the graph we have seen earlier. Grids are general types of plots that allow us to map similar or different plot types to row and columns of a grid. This basically instantiates the figure object and plots the axis on that, and then we can plot whichever way we want to on them. So basically it creates a plot like subplots, and then we can plot the customized graph on those subplots. So here we have two kinds of grids, pair grid and facet grid. Pair grids are used for pair plots. These are the base of pair plots, and then in place of Seaborn automatically placing the plots on those, we can select the type of graph we want on those grids. And similarly, we have a facet grid which will create rows and columns for the categorical data in our data frame, and then we can plot the graph we want on those based on the rows and columns. So first, for the grids, we will use a new data set called iris. Iris is one of the most famous data set in the data science circle. To load this, we can use sns.load underscore dataset and pass in iris. And let's check the head of this. So here we have a column called sepal length, sepal width, then we have petal length, petal width, and then species. So these are basically kinds of flower, and we have the length and width of the sepal and petal with us. So let's check the info to get more information about this data set. So here, as we can see, there are a total of 150 entries ranging from row index ranging from 0 to 149, and then there are 5 columns. As we have already seen, there are no null values. The first 4 columns are all float data, and then the species is an object. So this is basically a string object here. If you want to further check this species column, we can do a value count here, dot value count. So as we can see, there are 3 different values in the species. Those are Setosa, versicolor, and virginica. These are the scientific names of the flowers, and there are 50 entries for each of those. So in total we have 150 entries in the data set. Now for a data set like this, earlier we saw how to plot a pair plot. Let's quickly check that as well for this data set. You can just pass in the dataset name and it will automatically plot. Yeah, so it's a variable, so we need to pass in without the inverted comma. And let me zoom in. Is it called zoom in or zoom out? Let me zoom out a bit so we can see the entire pair plot. Yeah, so here we have our sepal length, sepal width, petal length, and petal width on both rows and columns. That is on both y-axis and x-axis. And the diagonal elements are histogram for univariate data, and then we have scatter plots for each pair of numerical data in that data set. So when you compare this sepal length to sepal width, we can see there are two different clusters here. Similarly, when you compare sepal length to petal length, once again there are two different clusters, and we see the same pattern with all of the x versus y comparisons here. Now let's say you want to customize this graph further. Rather than using pair plot, what we can do here is we can use pair grid. So a pair grid is a subplot grid for plotting pairwise relationships in a dataset. A pair plot is the simpler version of pair grid. So what we saw here, we will get our subplots with the same variables on the y and x axis, but we can customize the individual plots here. So the command for this is sns.pairGrid. Uh, Notice the capital P and capital G here for the pair grid, and then we can pass in our dataset name, run this. Let me zoom out again so you can see the entirety of this pair grid. So as you can see, on the x-axis we have all of the same variables as on the y-axis, which we had earlier for the pair plot. Now what we can do here is set this as a variable. Let's say this is equal to g. So if you call g, we will get the same pair grid, sorry. And then we can map on this. If you use map method and press tab, you will see we'll get these options for map underscore diagonal, which will map on this diagonal subplots. Then we have map underscore lower. We select the subplots which is below this diagonal line, and then we have map underscore occur, which selects all of these subplots which is above the diagonal line. So we will use all three of these. We will customize one kind of plot for the diagonal, which would be univariate data. Then we will use another kind of plots for the upper, for x versus y comparison. And because we already have the same comparison, we will use a different kind of graph for the lower. Let's go with map underscore diagonal. Here we can pass in the name of the plot which we want. So if you look at the doc string for this map underscore diagonal, we have to pass in the function, and then we can pass in other keywords as well, which goes with that function. So this plots a univariate function on each diagonal subplot. So let's check what this gives. So what we have here is we have our histogram for univariate data. If you want KD plot on top of this as well, you can use the keyword KD is equal to true. So we have that. Now let's say we want to plot on the upper diagonal. So we can use g.map, select map underscore upper, and then let's say we want scatter plot on this. So we can use plt.scatter for that, run this, and so it will plot the scatter plot for all of these x versus y variables. Now since we already have the sepal length versus sepal width, we don't want uh, a plot for sepal width versus sepal length. We will just be inverse of this graph here. So rather than that, if you want to see a different kind of graph to see the relationship between sepal width and sepal length, what we can use here is map underscore lower, and then pass in, let's say we want a KD plot for this. So see, KD plot is different from this scatter plot. And now if you compare this to the pair plot which we plotted earlier, Let me go back up. We have the exact same graph on the diagonal and on the upper subgrids, but if you look at the lower subgrids, we had scatter plot there, which will just the inverse of what we have here. The data was just the inverse of what we have on the upper subgrids. So here we have a different kind of subplots, and we can analyze the data using two different plots here. So this is the benefit of being able to customize the graph on the pair plot using a pair grid. So now that we have our pair grid, let's move on to the facet grid. A facet grid is the general way to create grids of plots based off a feature or a categorical data. Feature is nothing but the categorical columns in a data frame. So it can have up to 3 categorical data divided as row, column and hue. So let's see this. Once again, see the F is capital and G is capital. Normally when we were plotting the other graph, all the letters were small. But when you are using the grid, either pair grid or facet grid or even joint grid, we won't cover the joint grid here, but it is just the grid for the joint plot which we had. So for facet grid, let's check the doc string. So here we need to pass in the data. Then we have an option for row. You can pass one of the categorical columns for that, and that will divide the plot for each categorical data. Then we have a parameter for column where you can pass in another categorical column, and then we have an option for hue as well. So remember, hue will separate the categories based on color combination. And then we have some parameters like height and aspect. This is nothing. Height is the height of the subplot, and aspect ratio is the ratio of height and width. So if it's 1, that means if you pass in height as 4, the width of the subgrid would be 4 as well. So let's pass in our data first. We will use our tips data frame for this. And then let's say for the row, we want to use the smoker column. Let's check the tips data set first. Let's check the head of the tips data set. So remember, we have two floating column for total bill and tip, and then we have 4 columns for categorical data, sex, smoker, day and time, and then we had a size column which is integers. It was just the number of people here. So let's say we want to divide on the row the smoker. The values for the smoker column are yes and no. So we want a separate row for yes and a separate row for no, and then we further want to divide the data by this time column. The time has categories lunch and dinner. So let's run this, and so this is what it gives. So on the rows, if you see, the top row is yes, smoker yes, and the bottom row is for smoker is equal to no. Similarly, on the column we have used time. So on the first column we have lunch, and the second column we have dinner here. Now, just like the pair grid, we can save this as a variable, and then we can map on that variable. So here, let's say we want to see histogram for total bill. So if you check the doc string, once again you can pass in your function and then keywords related to that function. If you look at the doc string for hist plot, the very first parameter is x. So we already have the data here. This facet grid is based on this data, so we don't need to pass in our data. We can directly pass in our column name for total bill. Let's run this, and we have our histogram for the data divided by smoker and with time on the column. If you want KD plot on top of this, we can pass in true for that, and it will plot the KD curve on top of the histograms as well. So see, this is very useful to analyze the data. Here we have already used one column from the data frame, divided that as rows. then we use another categorical column and divided that as column, and then we have the ability to further divide it as hue as well. Let's plot another facet grid and we will check. So let's say for the same data set, so for row we have smoker, for column we have time, and let's say for hue we will pass in sex. And now we will plot scatter plot for this plt.scatter. For scatter we need two variables, x versus y, so you can pass in total underscore bill. Will be for x axis, and then for y axis we can pass in tip. So let's check this without, so hue has got nothing to do with it. X and y must be the same size. So you cannot pass in y is equal to, because that parameter doesn't exist under map. You directly have to pass in the functions here. For scatter plot you obviously need x and y, and you can directly pass in your columns here. So here as you see, the graph is already divided for smoker on the rows, and then it is further divided by time data for columns, and then we divided it based on sex, based on colors. So we have so right now we don't know which color this blue and orange represent, so we can add in the legend for this. So here we know blue is male and orange is female. This is same for the entire data set. You can also give a location for this, and we'll move it outside. There's another way of doing it. You can directly add it here. You can use underscore add underscore legend. Run this and it will come outside. So here we have blue color for male, orange for females, and you can distinguish between male and female data on the scatter plots itself. So next we will move on to the regression plots. Now Seaborn has many built-in capabilities for different kinds of regression plots. However, here we will focus only on the lmplot function for now. Lmplot is used to display a linear regression model which estimates the relationship between two or more variables by using scatter plots and plotting a straight line through those. However, lmplot also allows us to split up those plots based off of features, as well as coloring the hue based off of features. So features are, like I said earlier, the features are just the categorical data. So we can once again use the row and column parameters to split the data like we did with facet grid, and then we have a hue parameter as well, where we can color code another categorical column. A regression analysis is used for making future predictions in many different fields like finance, economics, stock markets of all the places, and then for market research and marketing, and most importantly it is used in machine learning based on historical data. So a regression plot will basically plot scatter plots and then pass in a straight line through the data based on the best fit, and then we use that line to predict where a certain y value would be given the particular x value. So let's see this for our data. The code here is sns.lmplot, and if you check the doc string, we need data, then we need to pass in x and y values, and then we will further divide it by hue, color and rows. So first for data, our data set is tips. Then on the X column, this is between two columns of the data frame, right? It's for the bivariate data. So on the X axis, we want to see the relationship between total bill, and on the Y axis, tip on the other hand. So let's run this, and here you go. So we have the total bill data on the x-axis and tip data on the y-axis. So for all of the data points, we have this scatter plots here. So what LM plot does is it plots this straight line through the scatter plots based on the base fit method. So let's say if you say the total bill would be $40 and $50, the probability of tip being somewhere in the range of $5 to $6 should be very high now, but not all of the values will fall exactly on this is a prediction which is based on high probability of being in that zone. So now let's say you want to separate it for both sexes. So in the hue we can pass in sex, and so it will color code the data for both males and females, and it will further have the NM plot line, the linear regression line for both males and females separately as well. Now let's say you are still having difficulty reading this data and you want to further customize it. You want to use different kind of markers for both male and female. For that we have a parameter called markers here, which is by default given as O, which is for a circle marker. So you can pass in marker. If you want just different kind of marker but you want it to be same for both male and female, we can just pass in a single string here. V is short for this vertical markers, or you can pass in plus as well. You can check in different kinds of markers online. Now if you want different markers for both male and female, we can pass in a list here. So let's say you want a circle for males, but for females you want a V. So here we have circles for males and triangular markers for females. Now let's say you want to increase the size of this scatter plot as well. For this what we can do is we can pass in a scatter keyword, because we don't have a parameter directly given here for the size of the markers. We have markers but we don't have size of markers here. But remember, this scatter plot is based off of the matplotlib scatter plot, and here we have a parameter for scatter underscore keyword. So you can use the scatter plot keywords with this parameter, but you will have to pass in this like a dictionary here. So we'll pass in this, and here you can pass in a dictionary. Remember, the marker for size in the matplotlib for scatter plot is S. So we will pass in a key value pair. The key will be this parameter, and let's say we want size 100. Now let's run this and you will get bigger size of the markers here. Now let's say rather than doing all this, you want to further segregate the data based on different categories. So let's plot another LM plot for that. You want data to be tip. On the x-axis we want total underscore bill. On the y we want tip. We have our LM plot. Now let's say you want, rather than using different color combination, you want the sex column to be different columns. So here we have two different subplots, two different columns for male and for female. Now let's say you want to further divide this based on time. Remember, time is lunch and dinner. So we can pass in, we can use row parameter and pass in time for that. Let me zoom out. Yeah, so here we have time is equal to lunch on the first row and time is equal to dinner on the second row. Similarly, the first column is for male and the second column is for female. So that gives us four subplots, and we have the data based on that. Now once again you can further divide this for hue as well. Let's say for hue we will pass in day, and this day will give us four different colors, which is very complicated. So what we can do here is we can pass, let's say we pass day for columns. This will give us four columns 2 rows, and then for hue we will pass in 6. So we will have different colors for both males and females. Zoom in. This is better. So if you see, on the x-axis we have total bill, but we have divided the columns by day. So here we have Thursday, then we have Friday, then we have Saturday, and then we have data for Sundays. Rows were time, so the top row is for lunch, the bottom row is for dinner, and then U is sex, so blue ones are male and orange ones are female. And looks like there's no data here for lunch for Saturday and Sunday, and similarly there's one data point for Thursday dinner time. As you can see, most of the data is for dinner time for Friday, Saturday and Sunday, and for lunch it's mostly on Thursday. Looks like the dataset doesn't have a lot of data, because any restaurant will have a lot more people visiting for both lunch and dinner on all days. So maybe the data is not complete here, but anyway it helps us to analyze the data here. And then if you check further, if you want to use a different color combination for the hue, you can pass in that as palette. You can check different palette options or different color combinations or CMap in Seaborn. You can Google that and you will get different combination names. And then remember, we have a parameter for height and aspect ratio, so you can change that as well. And there are so many other parameters given here. These are for advanced uses. If you want, you can read this. The detail of those parameters are also given below, so you can just go to the docstring and read this in detail. Most of the time you won't need that. It's only for advanced users. If you want to further customize your graph, you can do it, but for basic analysis this should suffice. Now, so next we will move to style and colors. So now that we have seen different kind of plots we have available under Seaborn, it's good to know that we can control the aesthetics of those plots as well. So while working with Seaborn, we can set particular styles, context or color at the start to control the figure aesthetics, and those will be followed automatically for the rest of the notebook. We have these different methods here: set underscore style, context, figure size and d-spine. So let's check those one by one. So first let's check the different styles we have available here. So here first let's plot a simple plot. We will use count plot. So data would be tips, and on the x-axis we will pass in the sex columns. So this will give us a simple count plot for the males and females. Now before this, if you type sns.set underscore and press tab, we will get this different options. We can to set different aspects of the graph. So for style, let's select that, press tab, check the docstring. So there are two parameters given here, style and none. So this sets the parameters that control the general style of the plots. So when you run this at the start of your session in the Jupyter notebook, whatever plots you plot after this, these set of arguments will control those plots as well. It will override the default options given on those plots. The style parameter controls properties like the color of the background and whether a grid is enabled by default. This is accomplished using the matplotlib RC params system. So for the style, we have four options here: dark grid, dark, white and text. This is basically the background of the plot we have here. By default, it is given as white. We have an option for dark and then white grid, dark grid and text. So by default, this style is given as white. So let's change this style to dark. And we have a dark background here. Let's say you want to use this dark grid. So dark will come with this grids. We have these lines which makes it easy to read the data. So right now we see this is more than 80 because the line passes just below the top of this count graph here. And then we have white grid as well. And there is an option given for ticks. So those ticks are basically this ticks which goes with the data. If you use just white, see we don't have those ticks here. So by default we had ticks here, not white background. Now for the same graph, let's plot this once again. We have count plot here. The data is tips dataset, and on the x-axis we have the 6 column. Now let's say you want to remove the spines. Spines are these outlines of this graph. If you don't want that, you can use the dspine method. Let's pass this, and you see by default it has removed the top spine and the right spine. If you check the doc string, we have our figure and axis parameters, and then what we have here is top is passed as true. So when you run this, it will remove the top spine, then it will remove the right spine, and left and bottom are given as false by default. So if you want to remove the left and bottom spine, you will have to pass true for those two parameters. So this removes the top and right spines from the plot. So let's say if you want to do that, let's say we pass in true for both left and for bottom, and so this will completely remove all the spines are nothing but the axis of the figure, and this is the kind of graph you will get if you want that without passing true for the left and bottom. Those are given as false by default, so those two spines will remain here, and you can remove the top and right spine using the dspine method if you want. Then after that we have a size and aspect ratio. So you can use matplotlib's plt.figure and then pass in fixed size parameter inside that to change the size of the most of the Seaborn plots. We can also control the size and aspect ratio of most Seaborn grid plots by passing in parameters like size and aspect ratio. So let's once again plot our count plot. Data is equal to tips, and on x-axis we have 6. So what we want to do now is change the size of this figure. So for this, what you can do is, before your codes, we can use plt.figure. This is from matplotlib, and pass in the fixed size parameter. And if you check the fixed size, we have width and height in inches. So let's say you want to elongate the width of this graph. What we can pass in is, let's go with 12 by 3. So now there will be more width and less height. Let's say you want more general kind of squarish looking kind of graph, we can go with 5 by 3. You can go with 5 by 3 here, 5 by 4 here, or let's say you want a little bigger size, you can go for 7 by 8, which is more taller. If you want a smaller size, you can go with 4 by 3. 4 by 3 would basically means it has more width than height. Let's go with 12 by 3. This will have a lot of width. The width will be 4 times as the size of the height here. So this is 12 inches by 3 inches. Now this will work for non-grid plots, but if you have a grid kind of a plot, so for that we can pass in the size and aspect ratio inside that. So if you go back to the LM plot which we plotted earlier, if data is equal to tips, x is total bill, y is tip, so this LM plot is basically built on top of a facet grid. And if you check the parameters here, we have an option given for height and aspect ratio, so you can directly change the size using those parameters. Let's say if you go for height 10, it will give us a very large graph. Because the aspect ratio is 1, so when you pass in the height as 10, the width automatically adjusts as 10. If you go for height 4, it will be much smaller. And then you can change the aspect ratio, which is basically width by height. So if you want half the width, you can pass in 0.5. So the width will be lesser than the height, or if you want double the width, you can pass in 2 here, and so it will have more width than the height here. So now one last thing I want to show you here is how to change the context. How to set the context here. So we have set underscore context method for that. Here we have parameters for context for font scale and RC is equal to none. RC is short for runtime configuration. So this sets the parameter that control the scaling of the plot elements. So these are based on level size, line thickness, etc. So for context, we have 4 different options given here. These are paper, notebook, doc, and poster. So poster will have the biggest labels, and the size of the labels and fonts increase as you go from left to right. So paper is for your own use. You can have smaller fonts and label sizes. Notebook is little bigger than that. That is, if you are sharing a presentation with a small group of people on your laptop, you can use slightly bigger font size and level size so that they can see. Talk is done if you are for a much bigger room. Let's say you are giving a conference and people who are sitting at the back of the room, they can see from there as well. And then the poster will have the much bigger font size and level size, so that you can post that, let's say, on a tree outside your building, and people walking far away from that poster should be able to look at that from quite a bit of distance and be able to read it. And then you can independently change the size of the font as well. So let's say pass in your parameter context, and let's go for paper first. Let's check paper, and so this is the size of fonts and labels we have. Now notice what happened when I pass in notebook for this. So now you have slightly bigger font and labels. Now if I pass in talk here, you have even bigger fonts and label sizes. Now poster would be the biggest of all. Now you can independently change the font scale as well. So one is this size. If you pass in 10 here, see how big it becomes. So let's go with some smaller size. Let's change it to 2. So see, the size of the font and labels become very big here. So let's bring it back to font scale is equal to 1, or we can further go back to talk. So you saw how we can adjust the different aesthetics of the plots. We can change the context to change the size of the labels and fonts here. Then we can change the figure size using fixed size parameter under plt.figure. If you do it at the start of your exercise, all of the figures you plot after that will be of that size until you change it again. We can also remove the spines, and we can set different kind of background styles as well using set underscore style here. Now that's all for the Seaborn. Now Seaborn is very useful for deeper analysis, but if you are working with a data set and you want very quick analysis just for your own purpose, then you can actually use the pandas library itself and quickly plot those graphs for your own quick analysis. We will look at those in the next video. Until then, thanks for watching.